All right. We're going to figure out a way to find the derivative of the natural log function, y equals natural log of x. And so hopefully you guys should all know that if you were to write each of these as powers of e, it should be the same, right? E to the y is equal to e to the natural log of x. We call that exponentiating this equation. We exponentiate it, as in make each of those a power of e, then it should be equivalent. It should still be equivalent. And then that would give us e to the y is just equal to x, because e to the natural log of x is just x. Everybody agree with that?
Mm-hmm.
All right, good. It's like you learned something last year. It's spectacular. So now what we're going to do is we're going to take the derivative of e to the y equals x, but we're going to do it implicitly. Oh, that's why we did all that implicit differentiation stuff first. So first off, we're going to take the derivative with respect to x of e to the y, and we're going to take the derivative with respect to x of just x. On the right-hand side, that should be awfully easy, right? What's the derivative of x?
1.
1, good.
1.
Yeah, and on the left-hand side, we're taking the derivative with respect to x of a term that has y's in it. We just take the derivative of that with respect to y. So what's the derivative with respect to y of e to the y?
E to the y.
E to the y. And then what's the derivative of y with respect to x? It's
Derivative of y relative to, yep, that.
Yep, that thing you're saying. Yep, that's what you were going to say. I know it. Dy dx, right? And so we end up with dy dx, or the derivative of natural log of x, is equal to 1 over e to the y. Now, our original equation was all in terms of x, right? It was a function of x. So we'd like, whenever our derivative, or whenever our function starts as a function of x, we'd like to have our derivative also be a function of x. So how could I rewrite 1 over e to the y?
You could replace the y with the l and x.
All right, we could replace the y with the l and x, or even, and that'll do the same thing that what I was going to do would do. But we also know just right off the bat that e to the y is equal to x, right? So we could just replace the whole e to the y with just an x. If we wanted to replace the y with l and x, we'd have e to the l and x, and that would just become an x also. Everybody see that? Or no?
Yes, we see it.
All right. Okay, well, you guys understand that? Makes sense? Not just see it physically, but.
Yeah.
Yep.
All right, spectacular. So the derivative of natural log is just 1 over x. So natural log of x, derivative 1 over x. We can apply the chain rule through that. So if we had natural log of u, or natural log of a function, what do you think the derivative of that should be?
1 over u.
1 over u, and then times what?
What u equals, or the derivative of du dx.
Times, right, times the derivative of u, exactly. So if we have natural log of a function, natural log of u, the derivative of that is 1 over u times du dx. And that's the rule you're really going to want to know, or just be able to apply the chain rule through your regular natural log derivative rule that we've now proven. Good or no? All right, we'll assume that's a good. So if we want to find the derivative of natural log of 3x squared, what should that become? Should become 1 over u, which is
3x squared.
3x squared, times the derivative of u, which is 6x.
6x.
And we should be able to simplify that down. The 6 over the 3 should just give us a 2. And the x over the x squared should give us an x in the denominator. So the derivative of natural log of 3x squared is just 2 over x. Everybody good with that?
Yep.
Here's a question just for fun. Could I use log rules to rewrite this? natural log of 3x squared. Couldn't I rewrite
Yeah,
this as,
add 2 to the front.
I can't actually yet. So that's, we're going to, but we can't take this 2 to the front yet because it's not, everything inside of the parentheses is not being squared. Only the x is being squared, the 3 is not being squared.
Oh, I see what you mean. Then you would have to like split it up.
Exactly. So we could write it as natural log of 3 plus natural log of x squared. Right? Isn't that the multiplication addition rule for logarithms? If it's multiplied within the logarithm, you can separate it as a plus in 2 different logarithms. And then now we can do what you were just saying with that 2 and bring that 2 out front. And if we wanted to take the derivative now, the derivative of natural log of 3, well, natural log of 3 is just a constant, right? So we take the derivative of that, it goes away, and then the derivative of 2 times natural log of x, right? If we take the derivative of this, we should just get 0 plus 2 over x. It comes out the same way if we use log rules, and we don't have to use the chain rule, but probably easier to just use the chain rule. How do we feel about that? Okay?
Yes.
All right. Spectacular. Let's do another one. The natural log of 5 times the cosine of 2x. This will be a fun one. So the derivative with respect to x of natural log of 5 cosine 2x. I don't know why I put so many parentheses on there. What should that become?
1 over 5 cosine 2x
All right, and then times what?
times
You need to do product rule.
We don't have to do product rule. We need to find the derivative of the 5 cosine 2x, which is chain rule, right? So the 5 is going to stay. And then we need the derivative of cosine 2x. And so what's the derivative of cosine 2x?
-2 sine x.
Right, negative, and then a 2, and then sine 2x. All right, so we'll write it out. It's 5 cosine of 2x. We could write it as 5 cosine u with u equal to 2x, right? So the derivative of 5 cosine u is -5 sine u times 2, or -10 sine 2x, -10 sine 2x. Everybody good there?
yeah.
All right, and how can we simplify that? We can get rid of the 5s, right? And then we just end up with a -2 and sine 2x over cosine 2x is tangent 2x. So the derivative of the natural log of 5 cosine 2x is -2 tangent 2x. Good or no?
Good.
A little bit of chain rule within the chain rule. Get used to the chain rule within the chain rule. It's going to happen a lot. It doesn't happen much on that first sheet, the chain rule that I gave you, but the one that I'm going to assign you on Monday to have due on Tuesday, it will. So, all right. So we've done this for natural log, but that's only one special case. We also need to be able to do this for a logarithm in any base. And hopefully, with any luck, you're familiar with the change of base formula. Anybody familiar with the change of base formula for logarithms? I hope. Maybe.
No.
No. Okay. The change of base formula says that if I have a logarithm in any base, let's say I have a logarithm of base 2 of 7, and that I can convert that into any base I want by taking the, let's say, it doesn't have to be natural log, but we'll convert to natural log by taking the natural log of the argument of the logarithm, so it's 7, and dividing it by the natural log of the original base for our function. So the log base 2 of 7 should be the same as natural log of 7 over natural log of 2. Should also be the same as log base 10 of 7 over log base 10 of 2. Or it should be the same as log base 1000 of 7 over log base 1000 of 2. You can convert to any base, a logarithm that's in a base, you can convert it to any other base by doing log of that argument divided by log of the original base. And that's the change of base formula for logarithms. Somebody should have taught you that last year, but I guess they didn't. So you're not going to need to know that rule. You probably won't ever have to use that rule in this class, other than right now to convert log base a of x into natural log of x over natural log of a. So if I have natural log of x over natural log of a and I want to take the derivative of it, how do I figure that out? What is the derivative of natural log of x over natural log of a?
You start with the
Quotient rule.
quotient rule.
Okay, we could start with the quotient rule. I'd rather us not if we don't have to, because what can you tell me about natural log of a?
The derivative should be 1 over a.
Is a constant.
It's a constant, right? Natural log of a is a constant. The natural log of any number is a constant, right? The natural log of x is not a constant because it's got an x in it, but the natural log of a is a constant because a is a number and the natural log of a number is still just a number. So really what we're looking at here is 1 over the natural log of a constant, times natural log of x. So it's a constant times a function. And how do you take the derivative of a constant times a function? You just write the constant, and then you take the derivative of the function and multiply them together. Now, some of you were saying the quotient rule, right? If we were trying to do the quotient rule, it would work. We would do the denominator, natural log of a, times the derivative of the numerator, which would be 1 over x, and then minus the numerator times the derivative of the denominator. Derivative of a constant is 0, all divided by the denominator squared. And so this whole term here would cancel out, and we'd have natural log of a over x all over natural log of a times natural log of a. And if we were to simplify that, these natural logs of a would come up here with this x, and one of them would cancel, and we'd end up with 1 over x ln a. So we can still use the quotient rule, but it's a lot easier to just treat natural log of a as the constant that it is, and just multiply it by the derivative of ln x. Everybody see both ways and good with that, or no?
So is the reason why we know a is a constant is because it's the base of the log?
Exactly, yep.
Okay.
Yeah. Any other questions on that, or everybody good there? All right, so we're going to use the chain rule with this rule also. So log base a of x is 1 over x ln a, but log base a of u is 1 over u ln a, and then times the derivative of u. So why don't you guys see if you can take the derivative of log base 3 of x to the 5th on your own. Take just a minute here and see if you can figure that one out using the chain rule. Everybody get an answer for that?
Yeah.
All right, so how do we do this? We did 1 over what?
X to the 5th
X to the 5th
times the natural log of 3.
times the natural log of 3. And then we multiply that by the derivative of our x to the 5th, which is 5x to the 4th. Then what do we end up with? 5 over x
5x.
ln 3.
Yeah.
Yeah.
Yeah, everybody go with that. Cancel off the x to the 4ths, and that's what we get. Now, could we have also used log rules first on this? Could we have written this as y equals 5 log base 3 of x? And then our derivative would have been 5 times the derivative of log base 3 of x, which would be 1 over x ln 3. So in this case, maybe using that log rules, it makes it a little bit quicker and easier. But either way is good. Any issues with that? Everybody see both methods there? Good with that?
Yeah.
All right, we're going to skip this because we've already talked. Oh, actually, we'll talk about this real quick. We talked about our derivative using the power rule, right? And that I told you at the beginning that it could be used for any real number, and that's true. And I actually want to make a short point about this from that first derivatives assignment. There was one in there that I think was x to the pi. And I saw a lot of people that wrote the derivative of x to the pi as something like this. Pi x to the 2.14. And so I want to make sure that if we're using an irrational number, we write it as pi x to the just pi minus 1. For our irrational numbers. So I'm not going to spend, normally I would spend some time proving why the power rule can be extended to all real numbers rather than just like whole numbers, but we're not going to bother. I just want to do a couple of these real quick. So something like x to the root 2, what would its derivative be?
Root 2x to the root 2 minus 1.
Right. And what about something like 3 plus 5 sine x to the pi? What rule do we have to use here?
Could we just use the power rule, or would we have to use chain rule also?
Yeah, have to use the chain rule within. This is u to the pi.
Okay.
So it should be pi times u to the pi minus 1 times the derivative of 3 plus 5 sine x, which is 5 cosine x. And then one other quick point I wanted to make also, now that I'm thinking about it, when I looked at that first derivatives assignment, there was one problem on there that was y equals e squared, and I told you to find the derivative of this. Anytime I put an e in here, I am not using e as a variable, and I'm talking about e as a constant. And so a lot of people said that the derivative of e squared, a lot of people said this, dy dx equals 2e. But that's not the case because e squared is a constant, dy dx should equal 0. So a lot of people messed that one up. I didn't type a comment in for everybody on that, but e squared is a constant. E to the 5th is a constant. Anytime you see an e in there, it's a constant, unless I specifically say I'm using e as a variable. Everybody good with that?
Yeah.
Yep.
All right. Okay, so now what I want to be able to do is I want to be able to take a look at a function like x to the x. So this one's a little bit different, right? We've dealt with x to a number, right, where we use the power rule. We've dealt with a number to x, where we use the rule for that, where it's 2 to the x times the natural log of 2, or 5 to the x times the natural log of 5. But now we have a variable being raised to a variable power. So any thoughts on how we can deal with that?
We just use power rule and just represent it differently.
Unfortunately, we cannot use the power rule. The power rule is only good for a variable being raised to a real number value. And since we have a variable raised to a variable, we cannot use the power rule.
Can you use logs?
How are you going to use logs? What are you going to do with a logarithm?
Maybe do like log base x of y equals x. I think that's what it is.
I see what you're saying. Okay, so we also don't want to normally put a variable as the base of our logarithm. That's a good idea. I like that idea. And you're on the right track with logarithms, but we don't normally use variable bases for our logarithms, especially because we don't have a way to differentiate a logarithm that has a variable base. We've only got a way to differentiate one that has a numeric value for its base.
Okay.
But you got the right idea with a logarithm. So, and you can use any logarithm you want of any base you want. And traditionally, we'll just use a natural log, just because it's less things to write. ln rather than log. We have natural log of y should be equal to the natural log of x to the x, which should let us rewrite this as natural log y equals what on the right?
X times natural log of x.
Exactly. And now on the right-hand side, do we have a function that we know how to differentiate with respect to x?
Yep.
What we would use the product rule, right? And then we use our log rule within it.
Yep.
What about natural log of y? Can we differentiate that with respect to x?
Yeah.
Yeah, we should be able to. We take the derivative of it with respect to y. So what's the derivative of natural log y with respect to y? Should be 1 over y times dy dx, right? Everybody good with the left-hand side there?
Yeah.
And then on the right-hand side, using the product rule, it should be x times the derivative of natural log of x, which is what?
1 over x.
1 over x. Plus, then we've got natural log of x times the derivative of x, which is just 1. Any issues with that? Everybody good so far? All right, so we've now got dy dx equals, I can multiply this y to the other side, y times x times 1 over x is just 1 plus ln x. Everybody good there?
Yeah. Wait, I have a question real quick. About the left side of the equation, the 1 over y.
Uh-huh.
I think I'm missing something there. Where does it get from the natural log of y to the 1 over y? Is that the
So that's we're taking the derivative of natural log of y with respect to x. So we take the derivative of natural log of y with respect to y, which should just be the 1 over y. That's just our log rule. And then we multiply it by the dy dx because we're taking the derivative of it with respect to x. That's our implicit. This is implicit differentiation, right? Does that make sense?
Yeah.
Okay. All right. So then we have y times 1 plus ln x, and y times 1 plus ln x is a little bit of an issue because our original equation was a function all in terms of x, and we'd like our result to be a function all in terms of x. So what can we do with this?
Replace y with x to the x.
Replace y with x to the x. So we have x to the x. That doesn't look like x to the x. X to the x times 1 plus ln x. And that's our derivative. Everybody good with that?
Yep.
All right. why don't you guys see if you can do this one on your own? So take a minute or two and see if you can figure this one out. How's this going? I had to go outside and yell at my kids being annoying for a minute. So you guys doing all right with this? Still need another minute to work on it, or are you guys ready to go through it?
One more minute.
All right. All right, so our first step should be to take the natural log of both sides. Which gives us natural log of y equals x ln sine x. Everybody do that first step correctly? Any issues with those first couple steps?
No.
Then we take the derivative with respect to x on both sides. So on the left, using implicit, that's 1 over y times dy dx. And on the right, it should be x times the derivative of natural log of sine, which should be 1 over sine, times the derivative of sine, which is cosine. And then plus the derivative of x, which is 1, times the natural log of sine x. So we should end up, as we multiply the y back over, our y is actually equal to sine x to the x. And x cosine x over sine x is x cotangent x. plus our natural log of sine x. Any issues or questions on that?
Where'd you get the x cosine x over sine x from?
So that's the first part of the product rule for x, ln sine x. So one function is x, and the other function is natural log of sine x. So it's x times the derivative of ln sine x, and ln sine x's derivative is the chain rule. So it should be 1 over sine x times the derivative of the sine x, which is cosine x. Does that make sense?
Oh yeah, I got it. Thanks.
Okay, then I got another one from the second step to the third step. So you're talking from here to here? Okay, yeah, so same thing I was just saying. So this is on the left-hand side, it's the implicit differentiation of natural log of y. So the derivative of natural log is 1 over the function, 1 over y, times the dy dx. And then, so I just was talking about this, but it's x times derivative of natural log sine. So there's your x, and then your derivative of natural log of sine, 1 over sine times the derivative of sine. So x cosine over sine. And then the second part of the product rule is plus natural log sine x times the derivative of x, which is just 1. Does that make sense? Okay, cool. And
so
then,
you did use.
Sorry, go ahead.
You can finish answering the question. I thought you finished. Sorry.
No, I was just going to move on to the next thing. So.
Okay, so you did use chain rule with that ln sine x right there?
Correct. Yep.
Okay.
ln sine x is natural log of a function, so it's got to be 1 over the function times the derivative of the function. Good or no?
Where did the sine x to the x come from in the last step?
All right, so we had a 1 over y right here. And so as we bring our 1 over y over to the right-hand side to just have dy dx, it becomes just a y. And since y is sine x to the x, we just replace it with that so that we're all in terms of x.
Okay, thank you.
Yep. All right, let's take a look at one more, and we're going to use this idea of logarithmic differentiation, which is what we've been doing in the last two, x to the x and sine x to the x, to differentiate this function, which we already know how to differentiate, right? What rule would we normally use to differentiate this?
Quotient.
Yeah, we'd use the quotient rule, right? But it's a little bit of a pain because both pieces of it require the chain rule. And suppose I added in also like a square root of 8x plus 1, and I added in a cube root of x minus 5, and down here I put in a 3x minus 7 to the 8th power, then it's going to become a real huge pain. Would you guys agree?
Yeah.
Yeah, we're not going to do that. But imagine that we had something like that. This method that we're going to use for the simpler one would be really nice. So we're going to take the natural log of both sides. Everybody agree that that should be the same thing?
Yeah.
Yeah.
Right. So if I have the logarithm of something divided by something else, I can separate that out into what?
Subtract them.
Subtract them, right? So natural log of y equals the natural log of 5x minus 4 to the third minus the natural log of 2x plus 1 to the 1/2. Everybody good with that?
Yep.
Okay, and then what can I do with the third power and the 1/2 power?
Bring them up front.
Bring them out front. 3 natural log 5x minus 4 minus 1/2 natural log of 2x plus 1. So far good?
Yeah.
All right, Cool. So now we can take the derivative of both sides. So natural log y becomes 1 over y dy dx. And then 3 natural log of 5x minus 4 becomes 3 times 1 over 5x minus 4 times the derivative of 5x minus 4. Everybody good with that first derivative part there? And then minus 1/2, and then it's 1 over 2x plus 1 times the derivative of 2x plus 1, which is just 2. Good or no?
Wait, at the end there, what rule did you use?
For 1/2 natural log 2x plus 1?
Yeah.
Yeah, so I left the 1/2 because that's a constant. And then it's natural log of u, so 1 over 2x plus 1, and then times the derivative of 2. It's just the log rule
chain rule.
with the chain rule. Chain rule with the logarithm one. Yep.
Okay, got it.
Okay. So then we can simplify what we got here as 15 over 5x minus 4, and then minus 1 over 2x plus 1. And we're multiplying all of that by what? To just get dy.
Thing.
Right, by our original thing, by y,
Mess up
which is
there.
this original thing, this little mess we had. And so this derivative is not what it would look like if you had done it using the quotient rule, but it's equivalent to what you would get if you did it using the quotient rule. And while it's not really nicely simplified, if you were just asked to like figure out what the derivative of this was at x equals 8, this derivative would be perfectly good enough for that, and it would probably take you a lot less time, I think, than trying to do it the other way, especially if I had, 7 other terms in that fraction there that were making it even more of a mess. So every once in a while they'll throw one question like this on the AP test, every couple of years. Haven't seen one in a couple of years, so you might see it this year, but this is called logarithmic differentiation. Everybody good with that or no? Any issues, any questions?
Nope.
All right, so let's move forward into something else. And we're gonna skip down here to this third page here. Yeah, third page here. You guys all see this derivative of arc sine page?
Yes.
Okay. Everybody familiar with the inverse sine function? At least vaguely familiar with the inverse sine function?
Yep.
You know that if you plug in something into it, you should get out an angle, right? Okay. So if we talk about the inverse sine function, y equals inverse sine of x, we could take the sine of both sides of this and get x is equal to the sine of y. Right? And all this stuff I've written up here is just restrictions on the domain and the range of sine and inverse sine that you should know from AIM 3 or Honors Pre-Cal last year, that restricting the domain of the sine function to negative pi over 2 to pi over 2 is how we end up getting the inverse sine function. That's not super important right now. So I'm not going to spend a bunch of time talking about that. But you should know that y equals inverse sine of x and x equals sine y are equivalent statements. Right? If I take the sine of both sides of y equals inverse sine of x, we get x equals sine y. Everybody agree with that?
Yeah.
Okay. So we're going to, on a new page here, we're going to differentiate x equals sine y implicitly. So here we have x equals sine y. Remembering that y is equal. This comes from y equals the inverse sine of x. So let's take the derivative of x equals sine y with respect to x on both sides. On the left side, what should we get?
1.
1. And on the right-hand side, what should we get?
dy dx cosine y.
We should get cosine y times dy dx. Good. And then we end up with 1 over cosine y equals dy dx. And this is not such a great answer because our original equation was all in terms of x, right? Y equals inverse sine of x. So we'd like to figure out a way to turn this into something that is all in terms of x. So take a second and think about that. I gotta deal with my kids for just half a second. I'll be back in just a bit. But think about how we can turn cosine y into terms of x. All right, any ideas on how we're going to turn that 1 over cosine y into something in terms of x?
Y equals
Can you
inverse
replace
sine of x.
y? Oh, yeah.
All right, I'm not sure what you, okay, you guys said replace the y with inverse sine of x.
Yeah.
So we end up with something like the cosine of the inverse sine of x. Yep, we could do that, and that's acceptable, but also really, really irritating looking, isn't it? I mean, how many of you like to deal with a cosine of the inverse sine of something as your derivative? Probably none of you. I'm going to go with none of you. So let's see if we can find a way to get rid of the trig functions completely. It's going to take a couple of steps here. Or in fact, actually, let's go back to what you guys had, because let's see if we can work from where you had it, since you guys did that first step. Maybe. You have 1 over cosine of the inverse sine of x. What does the inverse sine of x mean? It means we can draw a right triangle here and call this angle y. Do you guys agree with that? If y equals the inverse sine of x and x equals sine of y, then we could draw a right triangle with an angle of y on it.
Yeah.
Okay. So if the sine of y is equal to x, how can I label parts of this right triangle? What can my opposite side be? What's the ratio for sine? Sine is the opposite over the
Hypotenuse.
hypotenuse. So if I have sine y equals x, then the opposite side should be x, and the hypotenuse should be
1.
1. True? Okay. Could I find this adjacent side using the Pythagorean theorem?
Yeah.
Okay. If I were to try to do that, what would I get? Let's call this A. We know that A squared. All right, yeah, so what did you get? You got A equals the square root of 1 minus
X, yeah.
Yeah, 1 minus
X
x squared. Yep. So if the inverse sine of x is y, what's the cosine of y? We got a right triangle here. What's the cosine of y? It's adjacent over hypotenuse, right? it's 1 over root 1 minus x squared. That is the derivative of the inverse sine of x, all in terms of x. Everybody see how we transition from cosine y, where y is the angle for a sine function that equals x, into 1 over root 1 minus x squared?
Yeah.
Okay. Anybody see another way we could do that? Just for fun, I'm going to show you. Couldn't we say that sine squared y plus cosine squared y equals 1? Isn't that a rule that we know? Pythagorean,
Yeah.
yeah, one of our Pythagorean trig identities. Right. So cosine y should be equal to the square root of 1 minus sine squared y, shouldn't it? Subtract the sine squared and the square root. Yeah. And what is sine of y equal to? Sine of y is equal to x, and that's the square root of 1 minus x squared. So we could have done it this way, or drawing it on a right triangle and figuring out what the angles and the sides are also works. Everybody good or no?
Yep.
All right, cool. So our derivative of inverse sine of x is 1 over root 1 minus x squared. And if we want to find the derivative of the inverse sine of a function, so instead of just having an x in there, what would we do? We'd use the chain rule, right? So we should be able to apply the chain rule through this derivative as well. Would you think you can do that? I hope. We're going to try it in just a minute. All of the other trig functions or inverse trig functions, their derivatives can be found using the same method, using implicit differentiation. We're not going to do them all. So here is the list of the derivatives of the inverse trig functions, and you need to know and memorize all 6 of these as well. And today, after class ends, I'm going to post up a sheet that has all of the derivatives that you should have memorized on it. So take a look for that up in the Google Drive. I'll also put it up in Google Classroom, but these 6 will be on it. So we'll note a couple of things. If we're looking at the inverse sine and the inverse cosine, they're the same, except that the cosine one has a negative sign, right? If we look at the secant and the cosecant ones, they're exactly the same, except that the cosecant one has a negative sign. And if we look at the tangent and the cotangent, they're exactly the same, except the cotangent one has a negative, right? So if you can remember sine and tangent and secant, then you should be able to remember the other 3. Just throw a negative sign in front of the co-functions, right? Sine and cosine are the same, tangent and cotangent are the same, and secant and cosecant are the same. Good or no? Everybody okay with that or not?
Yeah.
All right. So let's find the derivatives of each of these fun functions, starting with the inverse sine of root x. We'll do that one together, and then I'm going to give you guys a couple minutes. We'll maybe do the first 2 together, and then I'll give you guys a couple minutes to try and do numbers 3 and 4. So if we've got the inverse sine of root x, this is the inverse sine of u, right? Where u is equal to root x. So the derivative of this should be the derivative of the inverse sine, which is 1 over root 1 minus u squared times the derivative of u. What's the derivative of root x?
One half to the x to the negative.
Right, 1/2 x to the negative 1/2, right? This is the one I told you guys to memorize, 1 over 2 root x. So what do we get? The root x squared is just x, so this is 1 over, we've got a 2, we've got a a root 1 minus x, and we've got a root x. Good or no?
All good.
All right, let's do number 2, then you guys can do 3 and 4 on your own. 3 and 4 get a little more complicated. So I'll give you guys a few minutes to work on that. All right, so what about inverse tangent of x squared? What's the rule for that one? You should have it on the previous page. The derivative of inverse tangent of u is 1 over 1 plus u squared. So the derivative here should be 1 over 1 plus u squared, and then times the derivative of u. So we should get 2x over 1 plus x to the 4th. Everybody good with that?
Yep.
All right, cool. So for the next 2, I'll give you guys about 3 or 4 minutes to work on those 2, and then we'll go through them. Don't stress about a bunch of simplification. Don't worry about simplifying so much. Just try and get the derivatives figured out. So take 3 or 4 minutes and work on those 2. How are we doing with those 2? Do we need another minute, or are you guys good? You guys ready to go over them or no?
Yeah.
All right. Let me give us a little bit of space here. So we got inverse secant of, what was it, root x squared minus 1.
Yeah.
So if we recall our derivative of inverse secant, it's 1 over absolute value u times root u squared minus 1. So we should have 1 over the absolute value of root x squared minus 1 times what? The square root of our x squared minus 1. Squared minus 1. Everybody good with that?
Yeah.
Okay. And then times the derivative of root x squared minus 1, which is using the chain rule, 1 over 2 root x squared minus 1, times the derivative of x squared minus 1, which is 2x. Everybody good with that?
Yep.
Okay. First off, the 2 and the 2 will cancel. So we're just going to have an x in the numerator for now. And then the absolute value of root x squared minus 1, the absolute value is kind of redundant there because we've already got it inside of a square root. So that's just square root x squared minus 1. And then over here, root x squared minus 1 squared is just x squared minus 1 minus another 1 gives us an x squared minus 2. And then over here, we've got the 2's canceled. We still got a root x squared minus 1. And we can then just turn that x squared minus 1 that's in the denominator into 2 root x squared minus 1 into just an x squared minus 1. How we feel about that, okay?
Yep.
All right.
Wait, where did you get the 2 from, x squared minus 2?
So right here, we had root x squared minus 1. We were squaring that within our square root. So that became just an x squared minus 1.
Oh, okay, okay.
And then we had the other minus 1 to make it 2.
Okay, thank you.
Yep. All right, what was the other one? It was the inverse, I think it was inverse tangent, is that right? Of sine of something, sine of 2x, 3x?
2x.
2x, okay. So inverse tangent means it's going to be 1 over 1 plus this sine of 2x squared, so sine squared 2x, times the derivative of sine of 2x. And using the chain rule, what's the derivative of sine of 2x? Should
2
be
cosine 2x.
2 cosine 2x using the chain rule. So let's put it all together, 2 cosine 2x over 1 plus sine squared 2x. Good or no?
Good.
All right. Let's see here. I don't think it's going to be much use to us to do a bunch of these like x times the arc cosine. And I should probably note that arc cosine is the same as the inverse cosine. Same with arc sine. I should probably talk about that. Arc sine is the same as the inverse sine. It's just another notation. They might use either one on the AP test. But I'm not going to go ahead and do this one. I mean, this one is just the product rule. Right? It's product rule of x times the inverse cosine of root 4x plus 1. Use the product rule and the new rules. Right? Same with these. Not going to bother doing these. I think you guys have the idea of it down, is my hope. Would you guys agree that you guys got that down? Or no? Got the idea of it down? Or do you guys want to do one of them?
We can do one of them just to solidify the understanding.
All right, sure. Let's do, what do you want to do? This one? Number 10, 11, 12. What do you guys want to do? Anybody have a preference? Cosine, tangent, secant?
Try this one.
Sine.
Cosine, I gotta make sense. We haven't done a cosine one yet. So we've got a function x and we've got a function arc cosine, and I'm just gonna write it as inverse cosine just because it's less to write. So you can interchange those on the AP test. But x times the arc cosine of root 4x plus 1 should be x times the derivative of inverse cosine of root 4x plus 1. And so the derivative of that should be a negative, first of all. and then it should be 1 over root 1 minus this function squared. And then we got to multiply by the derivative of root 4x plus 1. So the derivative of root 4x plus 1 is 1 over 2 root 4x plus 1. And then we got to multiply that by the derivative of 4x plus 1 using the chain rule again. Everybody good with that?
Yes.
And then the second part of the product rule should be plus the derivative of x, which is 1, times the other function, inverse cosine of root 4x plus 1. And so the right-hand side's pretty straightforward. Left-hand side, we can simplify a bit. The 4 and the 2 are just going to give us a 2 in the numerator, and we got a negative and an x up there. So we're going to have negative 2x over, and here we've got 1 minus root 4x plus 1 squared. So that root 4x plus 1 squared just becomes a 4x plus 1. So this is root 1 minus 4x plus 1 inside parentheses. So 1 minus 4x becomes a negative 4x, and the minus 1 will cancel out with the other one. So this just becomes the square root of negative 4x. And here we've got the square root of 4x plus 1. Everybody good with that so far?
Isn't that an issue that there's a negative under the square root, or
That's fine. It
really
just
our
means
issue?
that's not an issue that we've got here, because as long as x is a negative value, then this will become a positive. So we would just have to look for what is the domain of this derivative. And if we're looking at the domain of that derivative, there's a lot of things that we have to take into account, like what's the domain of our original function? Well, root 4x plus 1, if we're talking about inverse cosine has to be a number between negative 1 and 1. So we'd go back in and we'd say root 4x plus 1's got to be between negative 1 and 1, and then go and figure out what x values make that true. And then we'd make sure that they applied down here and still made this exist. Does that make sense?
Yeah.
Yeah, but we don't, in this particular problem, we don't need to worry about that. And I don't foresee an instance this year where we'll have to worry about that with something like this. But one thing we can do is we can pull that 4 out and just make this a root negative x down here. And a root 4x plus 1. And if I pull out the 4, it becomes a 2 out here, and I can cancel it with that too. So we can have negative x in the numerator. So we can at least write this. But yeah, don't worry about having a negative inside your square root. If there's a variable attached to it, it just means that your x values are going to have to be negative. Any questions on that? Or anything else we've done today? I think we're almost out of time here. All right.